Now let's solve another sample problems. So in this sample problem, we consider cantilever beam, but in addition to this cantilever beam with distributed loading, where Wx changes as x over L W0, we have redundant simple support at the left hand. Okay, because of this redundant support, we happen to have 1, 2, 3 unknown reactions, Fa, Fb, and Mb. Yeah, this is B point, this is A point. Okay, and because we can have only two mechanical equilibrium equation, force equilibrium equation and moment equilibrium equation, we cannot solve this problem with statics. Okay, I mean statics means freshman physics. Okay, so to solve this problem, we needed the information about deflection, and as you can see, we didn't account for deflection back in statics and back in freshman physics. Okay, so deflection can only be handled in the chapter of beam deflection, and that's why we introduced beam deflection in quite later stage compared to chapter 5. Okay, because in chapter 5 we have already learned how to obtain mx and vx, but we haven't considered the statically indeterminate problem until now. Okay, so let's move on. So we have to find like more boundary conditions. So we have 3 unknowns and only 2 equations. So to find the more boundary condition, we have to first obtain the moment equation, and out of moment equation we have to obtain elastic curve, and we have to apply boundary condition to that elastic curve and moment and other quantities. So let's take some imaginary cut, and at this imaginary cut, and considering this blue point, we can try to get momentum summation, and summation of momentum should be 0. So we have locally mx moment, and out of this distributed loading, we can obtain the contribution of those torque by taking the center of weight and taking the distance, which is 1/3 x. So we have counterclockwise moment due to that red distributed loading, and from this green FA we have clockwise moment, so we add minus FAX, and they must be summed up to be 0, which gives us m as a function of x. So starting from m as a function of x and EI y double prime, we do integrate twice, 1 and 2 double integration. After double integration, we have 2 more unknowns, C1 and C2. So initially we began with 3 unknowns from statics analysis, and after moment and Euler-Bernoulli equation analysis, we add 2 more unknowns, C1 and C2. So how many boundary conditions can we have? So at x equals 0, when x equals 0, we have simple supported beam. So here y equals 0 and m equals 0, and when x equals L, we have y equals 0, dy dx equals to be 0. Okay, so we have 4 unknowns. However, out of this not 4 unknowns, 4 boundary conditions, out of these 4 boundary conditions, this is not useful because m equals 0 at x equals 0 is already in this derivation, so it's not very useful. But we have 1 and 2 and 3 boundary condition that is still independent and useful. And in addition to that, we originally have 2 mechanical equilibrium equation regarding force equilibrium and moment equilibrium. So out of these 5 equations, and out of these 5 unknowns, we can uniquely determine C1, C2, FA, FB, and B. Okay, so I'm gonna leave that solving these equations to your job, but after solving this equation, you're gonna have FA and C1 and C2 value, and you will be able to obtain the elastic curve equation y as function of x. Okay, so this is a problem concerning uniformly changing distributed loading. So here we can consider a little bit more simpler problem. Instead of wx as function of x, we consider wx equals to be constant w. Okay, so other than that, this problem flips the rigid wall into left side and change the simple support to the right side. Other than that, it's identical problem except this condition. Okay, so even for this problem, we have 2 mechanical equilibrium equation. Yeah, you can derive this by yourself. Okay, but because of this redundant support, we have three unknowns: MA, FA, and FB. So we cannot determine MA, FA, FB three reactions out of statics. So our strategy is find M as a function of X and try to apply the boundary conditions. So to find this Mx, we take imaginary cut here, and with respect to this black point, we obtain summation of M, and after considering moment summation, we have several terms, and out of this summation of several terms, we can obtain M as a function of X, and Mx somehow include our unknowns MA, FA, and that's it. Yeah. So after obtaining Mx, because this is related to y double prime, we do perform integration twice. After doing double integration, we are adding two more unknowns, C1 and C2. So we originally begin from three unknowns, but we add up two more unknowns, and our job is to find the boundary condition. Okay, so at x equals 0, this cantilevered beam, we have two boundary conditions that is useful, y equals 0 and dy dx equals 0. At x equals L, we have two conditions, m equals 0, y equals 0, but m equals 0 condition is already represented in the expression of mx, so only y equals 0 at x equals L is the another useful information. So we have three useful information, and we have two mechanical equilibrium equation regarding force and moment. So we have total 5 linear equations, and we have total 5 unknowns, and we can find the solution of this problem. We are guaranteed to solve this problem. However, we found that it is a little bit problematic. Like, we found that it takes quite a long time to solve statically indeterminate problems concerning beam deflection. Okay, so of course I will not able to make a final exam problem out of these kind of problem solving method, because I don't want to waste your time solving for 7 unknown 7 coupled equation, or 5 unknown 5 coupled equations. Okay, but what I'm gonna do is I'm gonna tell you another way, another efficient way of approaching the statically indeterminate problem, and then you can get some of this problem as one of the final exam problems. Okay, so in the next class, as an efficient method will I will just tell you how to use superposition principle to solve this problem. Actually, if you recall chapter 2 and chapter 3, we have learned how to use superposition principle to solve statically indeterminate problem for axial loading and torsional loading, and we're gonna do similar thing for beam deflection lecture. Okay, so with that, let me finish today's lecture, and we're gonna continue our discussion in the next lectures. Okay.